Hello. In the last lecture, we discussed introduction about flow through porous media. In particular, we discussed some basic models as governing equations. The first model that we discussed is a Darcy equation, which indicates that the volume flux is proportional to the pressure gradient. And in the second, we discussed about Brinkman equation. So, where you have viscous terms. And then we discussed about various possible interface conditions. And if you recall, the exact set of interface conditions at a porous liquid interface is really not settled yet. So, there are popular set of boundary conditions, and then these are well accepted in the literature and it is used. So, today we are going to see some simple configurations. Like in case of clear flow channel, already we discussed flow between two parallel plates and flow inside a tube, etc. So, similar models, however, in this case we are going to see with some porous packings. Okay. So, let us look at it. So, the first case is flow in a horizontal channel filled with porous medium. So, as usual, we are considering a steady viscous incompressible flow. So, this is the corresponding equation of continuity, and then we are going to discuss while assuming a Brinkman equation for the flow inside the porous media. So, this is the pressure force and this is the viscous force, and this is the corresponding damping by virtue of the porous obstructions. So, we have discussed a bit about this mu prime is called effective viscosity, which is in general is supposed to be different from the dynamic viscosity mu, but as I mentioned, various studies consider many of the times these two are equal, but there are some correlations, we will discuss about that. So, K is the permeability. Okay. So, then here for a generic setup in 2 dimensions, this is the seepage velocity of the fluid, okay, and this already I have indicated, and K is the permeability of the porous medium. Okay. So, let us consider the configuration. So, the first problem that we are going to discuss is flow bounded by 2 plates, and we have a porous packing, and we are discussing flow inside. And as you can see from the configuration, both upper and lower plates are impermeable. So, naturally we expect no slip condition there. Okay. So, with this configuration, if you recall, for clear flow we have considered a unidirectional case and then reduce the corresponding governing equations. So, the same we are going to do here. Okay. So, first assumption is flow is unidirectional. So, correspondingly we have u comma 0. Then once we have this from equation of continuity, we get u is function of y alone. Okay. So, then the corresponding x momentum reduces to this, because dou u dou x is 0, from the Laplacian term we get only one of the terms, other term vanishes. Okay. So, then the corresponding y momentum, since v is 0, we get the net inference is p is function of x alone. Okay. So, this is completely analogous to the flow inside parallel plates in case of clear flow, except that we have an additional term which is due to the resistance offered by the porous packing. Okay. So, naturally if somebody takes k goes to infinity, that means it is a large permeability. So, this vanishes and the equation reduces to clear flow Stokes equation. Okay. So, with this we are assuming for simplicity mu dash equals to mu, that is effective viscosity equals to the viscosity. Okay. So, now with this assumption, let us try for the solution. Before we compute the solution, we set up the boundary value problem by fixing the boundary conditions. So, at the upper plate the no slip condition u is 0, and then so if you see the configuration, what we have is say this is minus h to h, because this gap is of size 2 h. So, therefore, what we are considering is either we can fix at y equal to minus h no slip, and then y equal to h no slip, and then solve the complete domain, or consider either upper portion or lower portion and then use a symmetry condition. So, in this case we are using the symmetry condition with respect to y equal to 0, and then solve the problem in the upper portion. So, correspondingly you can see the boundary conditions. So, this is the no slip on the upper plate, and this is the symmetry condition at y equal to 0. So, du dy is 0. Okay. So, this sets the boundary value problem. Now, if you consider, since u x is 0, so this is the total derivative, and since u is function of y, so the left hand side is completely function of y, and then since we have p y is 0, that is a dou p dou y is 0, p is function of x, that is the inference we have. So, therefore, this is function of x. So, each must be constant. So, hence dp dx is a constant. So, this is again exactly analogous to the clear flow scenario. Repeatedly I am telling, so you have the damping force due to the porous packing, and then naturally when we non-dimensionalize, we expect some parameter controlling the permeability structure, and then we expect some limiting scenarios. Okay. So, the mean velocity in this case is given by, so we are integrating the velocity u across the domain and normalizing by the corresponding scaling. Okay. So, this is the mean velocity. Now, let us introduce non-dimensionalization. So, since we have only one length scale involved, so that is the spacing between the plates. So, this is x and y both are normalized by h, and then this is some characteristic velocity. So, u bar in this case is the mean velocity, and the pressure. So, the corresponding non-dimensionalization is already been seen in case of clear flow. So, one parameter that is additional here is not seen yet. So, if you see in the last lecture we indicated that the permeability k has dimensions of length square, and then if you see here we are normalizing by length square. Hence, this particular parameter, which is denoted by dA, is supposed to be non-dimensional parameter, and it is called Darcy number. So, let us see the non-dimensionalization and how we can get this Darcy number in our governing equation. So, let us consider the governing equation. So, which is mu d square u by dy square equals dp dx, and we have the non-dimensionalization given by x is x by h, y is y by h, and p is p by mu u by h. Okay. Of course, u is u by u. Okay. So, I mean I am not using primes, so just it is indicative. So, these are the non-dimensional. So, now let us non-dimensionalize. So, we have mu. So, now we supply u by, so therefore, there will be a u bar, then so we get h square there. Okay. Then k we are keeping as it is, then p by h. So, here we get then okay. So, now we try to simplify. Okay. So, this is non-dimensional velocity. So, non-dimensional quantities. Okay. So, with this if you simplify what the common factor is, let us say you normalize by h square by mu u. So, that means we are multiplying by h square by mu u throughout. So, this equation if you multiply throughout, what we get is the following. So, here this will be 1. So, therefore, we get, so this is normalized. So, I am not, so this is a normalized quantity, therefore, I am just we could have written primes, but I am just as a notation just we have dropped the primes. So, now look at this quantity. So, you have mu u bar by k and we are multiplying by h square by mu u bar. So, mu u bar get cancelled and then we get h square by k u equals, and here also we have exactly mu u bar by h square. So, you get, so this can be written as, you give a notation some alpha square u. Okay. So, where alpha square is h square by k. Still you might be wondering where is the corresponding Darcy number that we have defined. This is nothing but 1 over dA. Okay. So, the non-dimensionalization of the corresponding governing equation introduces a non-dimensional parameter, okay, which we are defining it as a Darcy number, or in this case 1 over Darcy number. Okay. So, if you see k goes to infinity, so that will be producing a Stokes equation, okay, large permeability case, right. So, this is limiting. So, now let us see the, that is what we have defined here. So, the non-dimensional equation just now we have derived, and alpha square is 1 over dA, where dA is k by h square. This is the Darcy number, and this represents the percolation inside the porous medium, because this is proportional to the permeability. So, large Darcy number means large permeability, small Darcy number means small permeability. Okay. So, we have a non-dimensional equation. So, now one can get the general solution and employ the corresponding interface conditions. Okay. So, this is a non-dimensionalized boundary condition. So, here there is no interface, you have a boundary, and then this is the symmetry condition, and the normalized volumetric flow rate is given by this. Okay. So, you will see how to use this volumetric flow rate, and then even while interpreting physical some physical insights, we come across the volumetric flow rate balance. Okay. So, it is very straightforward to write down the general solution, because we have dp dx is constant. So, one can get the corresponding solution in this form, where C 1 C 2 are constants to be determined using the boundary condition. So, now imposing the boundary condition, we get these constants, and once we determine u with the help of these constants, this can be utilized to estimate the pressure gradient, which is given by this. Okay. So, total volumetric flow rate balance is used to estimate the pressure gradient. Okay. So, now we have the solution. So, we would like to do some analysis. Okay. So, the compact form of the velocity can be represented like this, right. So, already I have indicated you have a porous packing. So, if permeability is large, we expect a clear flow scenario. So, if permeability is small, so then no flow, right. So, permeability large case, we would like to compare our results with plane Poisson flow. Okay. So, let us see. So, this is the Darcy number. So, for large Darcy number alpha is much less than 1. So, these two are equivalent, like the asymptotic case of dA goes to infinity or alpha goes to 0. So, the flow behaves like a clear flow channel. So, this is one can verify. So, let us see. So, the solution contains some hyperbolic functions. So, for large dA alpha is much less than 1. So, we can do some asymptotic analysis and consider this approximation. So, these are the hyperbolic functions involved in the velocity field. Okay. So, once we have these approximations, you substitute and consider the corresponding limiting case. What you get is alpha is much less than 1, right. So, if you take a corresponding limiting case of alpha going to 0, so what we get is exactly the plane Poisson solution. Okay. So, large Darcy number, the solution gives this. Okay. So, that is the limiting case, one can verify very easily. So, this is as I indicated, this is the plane Poisson flow. Okay. So, now once we have this asymptotic agreement, so we would like to see some results. So, the solution depends on the because it is non-dimensionalized. So, the only parameter that controls is the Darcy number. Okay. So, you will see the velocity with the y coordinate. So, here you see these legends indicate the Darcy number. So, this is a small, that means this represents a low permeability and this represents a high permeability. So, if the permeability is less, then what you would see is the resistance is more. So, the velocity will be less. So, you can see the velocity is less, and moreover you have the corresponding plate is here, because y equals to 1. So, here the interface viscous effects are more. So, the velocity is low here compared to the center of the channel. Okay. So, this is only one portion we are showing. Okay. Right. So, if you increase the Darcy number, so then you expect more flow. So, you see the velocity is increasing, then towards the boundary it is meeting the no slip. Further you increase, so then the velocity at the center it is increasing. Okay. And further if you increase, so this is almost you are reaching the fully developed clear flow channel. Okay. But you can analyze a little bit more. You see here for a particular Darcy number, suppose you consider a particular Darcy number. So, the flow behavior is the flow velocity is more towards the center and less towards the boundary. But if you compare two particular Darcy numbers, let us say these two, so this and this. So, towards the center, if the Darcy number is less, towards the center velocity is less, and if the Darcy number is more, towards the center velocity is more, but towards the boundary there is a crossover, and for low Darcy number it is more. Okay. So, this is because total volume flux is balanced. So, whatever amount is low here, that is being adjusted here. So, this portion plus this portion is conserved. Okay. So, that can be seen very clearly, and you can see one itself is onset of agreement with the fully developed case. Now, further if you take a large Darcy number and then you superimpose the clear flow solution, so they have a complete agreement. Okay. So, dA 1 onwards it is almost converging to the clear flow solution, and once it is dA 10 you have complete clear flow channel flow solution. Okay. So, this is so this case is this is a low Darcy number, that is a hyper means you can so hyper either way you can hyperporous and hypoporous you can define. Okay. So, that is like a highly porous and then a low porous you can define. Okay. So, this is the agreement with the clear flow channel for the parallel plate. So, quick inferences already we discussed. Increasing Darcy number increases the percolation rate, thus increases the velocity, which we have already seen. And for very large Darcy number, flow is in line with the clear flow. So, this is already we have seen, and maximum velocity occurs at the center of the channel. So, this we have seen because you see maximum velocity for any given Darcy number maximum occurs towards the center, because the boundary viscous effects are less towards the center. Okay. And the most important observation is the velocity increases with the Darcy number near the center due to less viscous effects, and it decreases with near the boundary due to the significant viscous effects, and to retain the volume flux this adjustment is taking place, this adjustment that I have explained. Okay. So, now we move on to the next problem. This is another simple elementary configuration that we discussed for the clear flow case. So, again similar to the case we are discussing flow inside a tube, but here we are discussing packing. So, this has a lot of applications, even though this is very elementary problem. So, lot of filtration processes they involve such geometries, and also flow through some tissues. Okay. So, you have veins which are like pipes, and then inside you have a lot of tissue involved. So, this gives some insights. Okay. So, let us look at the corresponding configuration and the governing equations. So, these are the same, this is equation of continuity, then Brinkman equation, and we consider effective viscosity equals to the dynamic viscosity. Now, in a cylindrical coordinate system, we have listed the corresponding component form. Okay. So, the Laplacian on VR, so this should be understood in terms of r theta z coordinate system, and this is the damping term. Okay. Okay. So, now we assume the fully developed assumption, that is flow along the axial direction. So, then with this assumption also you have axis symmetry. So, we have seen for clear flow. So, it is a more or less similar analysis. So, equation of continuity gives that V z is function of r and theta. Okay. So, correspondingly axis symmetry brings it from r theta to r alone. Okay. So, that is now r component, theta component, they ensure that p is independent of r and theta. Okay. So, this is the z component. So, essentially we have to solve this particular equation. Okay. So, this too ensures that p is function of z alone. Okay. So, now we have to solve this equation. Okay. So, without this already we have obtained. So, now you have an additional term. So, that will change the structure of the solution. So, like previous case, that is what we have seen. So, earlier we were getting only polynomial, but in the Brinkman case for channel flow we got hyperbolic functions. Similarly, for pipe flow without this we would have got a solution in polynomials in terms of r, but here we are getting something, we expect something else because of this. So, we do the usual boundary value problem setup. So, on r equals to a, no slip condition, and then regularity condition at the center of the tube. So, we do not allow any singularities. So, flow is bounded at r equals to 0. So, therefore, correspondingly we have this. Okay. And this is the mean flow. So, this is a very so, we would like to compute the mean flow. Okay. So, what we are taking a cross section, and then we would like to compute the mean flow. So, that is nothing but, so u along this area divided by area. Okay. So, corresponding areal element what we get is, so this is u r dr d theta. So, theta is 0 to 2 pi, r is 0 to a. Okay. and then correspondingly. So, this is 2 pi a square. Okay. So, once you integrate, so you get 2 pi get 2 pi will be getting cancelled. Okay. Oh, this is the area. Okay. So, once we integrate, so we get 2 pi by pi a square integral 0 to a u r d r. So, this will be 2 by a square u r d r. Okay. So, therefore, we get this is the mean velocity. Okay. So, again we non-dimensionalize, then we get this equation. So, with this no slip and the regularity condition, and this is a normalized volumetric flow balance. Okay. So, as I indicated, the solution is no longer polynomial in R, rather we are getting something interesting. So, this involves Bessel functions. So, these are modified Bessel functions of first and second kind of order n, but here we are getting of order 0. Okay. So, these are the modified Bessel functions. So, then we use regularity condition and the boundary condition. So, if you see, so this is bounded at origin and this is bounded at infinity. So, since our regularity condition requires flow should be bounded at origin, so therefore, this coefficient has to be killed, because this is bounded at infinity, this is bounded at origin. Okay. So, therefore, our requirement is flow should be bounded at origin, because interior flow. So, this coefficient must be forced to be 0. So, that we have this contribution, and using no slip we can evaluate, and this is the corresponding solution. Okay. So, again using volumetric balance, one can determine the pressure gradient. Okay. So, with this we have the velocity. So, now you may ask again whether we get the corresponding limiting case. Of course, we get. So, for the plane parallel plate channel case, I have shown you the corresponding asymptotic expansion of hyperbolic functions with large Darcy case. So, one good exercise here is you consider large Darcy case, that is alpha small, and then expand these modified Bessel functions. So, this is of order 0 and 1, and then take the limiting value to see that this solution indeed agrees with the Hagen-Poiseuille flow. Okay. So, that is a good exercise one can do. So, now similar to the parallel plate case, we have already explained. So, similar phenomena is happening here. So, this is a low Darcy number and this is a high Darcy number. So, correspondingly the velocity is getting adjusted, and then correspondingly the total volume flux remains constant. Okay. So, the viscous effects are more prevalent near the boundary, and the maximum velocity is at the center of the tube. Okay. So, you might be wondering, we are showing. So, we are showing only the portion, right. So, only this portion is plotted. So, that is what you are seeing in these plots. Okay. So, this is the competition with varying Darcy number, and with large Darcy number you have a complete agreement with the Hagen-Poiseuille flow. So, this is the Hagen-Poiseuille flow, real flow solution. Okay. So, corresponding analytical solution, you should take the limiting case and then check it. So, again results, magnitude of velocity increase with the Darcy number, and the solution is agreeing with the Hagen-Poiseuille flow in case of a large Darcy number, this we have seen, and maximum velocity at the center of the tube, and the velocity increases at the center and then decreases at the boundary, and the total volume flux balance is readjusting the velocity profiles with varying Darcy number. Okay. So, this gives some insights about elementary geometries, how the corresponding physical insights are differing compared to clear flow and then porous packed plate or tube. Okay. So, there are lots of applications where instead of complete porous you can have partially filled porous, and then these are typically having lot of applications. For example, if you take a glycocalyx layer in a human body or any animal body. So, glycocalyx layers are where you have a clear flow and then a porous layer coating. So, it is like a tube. So, then you have various blood cells migrating in it. So, these are like one can discuss microparticles transport inside channel, etc. So, before we really discuss such application, so in coming lecture we discuss about composite channels, that is partially porous and partially this clear flow. Okay. So, until then, thank you.